All right, everybody. If you have not turned in a trivia sheet, bring it to the front right now.
The microphone. Do you prefer? Are you a walker? Do you prefer to hold the microphone?
I am a walker, yeah.
I'll unwind it.
Do we have a slide changer or whatever?
Oh, yeah.
Okay, all right. Because I just realized I need to change slides at some point. I think so. Cool.
Forward, backward, and that's a logo.
Right.
All right, I'm going to assume at this point that everybody has their trivia sheets up. Meredith's going to get to work grading those and results for you at intermission. Until then, we have our first talk of the night by Pedro Bernardinelli, who is a postdoc at UW at the DiRAC Institute in the Astronomy department. Pedro was born in Sao Paulo, Brazil, completed his undergraduate studies in physics at the University of Sao Paulo, got his PhD from the University of Pennsylvania, and works on the development and application of new techniques for the discovery and characterization of the most distant bodies in our solar system, in our Trans-Neptunian objects, and he's a member of the Dark Energy Survey. All right, so give a big round of applause for Pedro. Talk of the night, and not just that, but our first talk in exactly 2 years. All right.
Hi everyone, good night. Can you guys hear me fine? My voice is a bit low. Louder? Okay. I don't know if you can adjust the sound here, but my voice is not that loud. So I apologize. They'll try to change something here. Let me just figure out that I can work this thing. Okay, I can. All right. Okay. Let me take the mic off so I can walk around, because I do that all the time. All right. So yeah, as it says here, my talk is going to be about how I, by mistake, discovered the largest comet ever found. The key takeaway here is that I was not trying to find comets, and I ended up finding one. So everything that I learned about comets was after I discovered this thing. So that's less than a year. So I was looking at the trivia questions. I think I could only get half of them. So yeah, if you got more than half, you know more about comets than I do. Anyway, so this is my mental picture of the solar system growing up. This is what we have there. We have the sun, and we have 8 planets. At some point when I was a kid, there was also Pluto, but it doesn't matter. Pluto's not a planet anymore. And yeah, this is kind of what I thought of the solar system when I was growing up. But it turns out that this is not a complete picture of the solar system. The solar system looks more like this. Each line and dot here represents one minor planet on the solar system. I think there are 1 million objects in this image. I'm not really sure. There's a lot going on here. And let me just point you a few things. So here is Mercury. This blue line here is the Earth. Then we have this thing, which is the Asteroid Belt. Once we go farther, we still have a few minor bodies. We have this region where the giant planets are, where we have a bunch of things. And then this faint blue line here is Neptune. And beyond Neptune, we have a bunch of stuff. And this is the region of the solar system that I'll talk about, which is called the Trans-Neptunian region. So let me show you a little bit of the history of the solar system. The solar system formed from a disk of gas and dust and etc. that was collapsing. From this collapse, the planets formed. And they didn't form where they are now. They formed in different places than their current orbits. And once this thing happened, these planets, we call it, there's a migration. They changed their positions, and they kicked a bunch of stuff around. In particular, they kicked things to the outside of the solar system, which is what we call this Trans-Neptunian object. And they also kicked things even farther in a region that we call the Oort-cloud. The Oort-cloud is one of the main regions where comets come from. So this is a little bit of what I'm going to talk about here. So we went from this thing to this thing in something like 5 billion years. And this is the modern view that we have of the solar system. So we have Earth. The Earth is 1 AU away from the sun. AU is the definition. 1 AU is the definition of the distance of the Earth. So I'll be talking about this thing. Every time that I say something AU, just think X times farther from the sun than the Earth. So I'm going to be talking about 30 AU all the time, which is the distance to Neptune. So that means 30 times farther from the sun than the Earth. We have the asteroid belt that I just talked about here. And once you go farther, we have a bunch of other objects. We have the Kuiper Belt and the Trans-Neptunian objects, which are in this region here. And then these things are still in somewhat of a disk shape. And once you go farther, we have a spherical cloud of objects, which is the Oort-cloud that goes as far as tens of thousands of AU. So for a reference, this is something like half a light year. So yeah, the Oort-cloud is pretty big. Just a little bit of historical context. First asteroids were discovered in the 1700s. The first Trans-Neptunian object, Pluto, was discovered in 1930, and the second one was only discovered in 1982. So it took us something like 60 years to start discovering these things, and now we know about 3,000 to 4,000 of those. Now, comets, I won't tell you how many there are because it wasn't the trivia, so if you got it right, you know the answer. Let me show you what these things look like. These two images represent the largest and one of the smallest objects in the Trans-Neptunian region ever found. This is Pluto, the dwarf planet, and this is Arrokoth. These two images were taken from the Kuiper Belt, from the Trans-Neptunian region, by the NASA New Horizons probe. So this thing was launched in 2008, if I'm not mistaken, and it took several years to get to Pluto. It took a few images of Pluto and then was maneuvered with some complicated stuff that I don't understand until it took images of Arrokoth. And this represents what these bodies look like in the solar system. So you can see that Pluto has lots of features. It has the pretty heart here, so there's a lot going on. And Arrokoth is also a very interesting shape body. It's a binary. It has this globe, and it has something like a 30-kilometer diameter. So you can imagine that there are lots of things going on between in this size. So this gives you a good idea of what the size of these things look like. And as I said earlier, we don't have all 3,000 of these things now. Now, comets look somewhat different from that. Comets are typically smaller. The whole reason here is that as they go closer to the sun, their material burns up. That's why we see them being pretty in images. You were showing an image of Hale-Bopp earlier, and you can see that there's the tail and the comet, etc. This is basically ice being sublimated on the surface. The thing gets close to the sun, the material gets hot, and then it evaporates. This is basically what's happening. And this image was taken from close to this comet 7B. I won't try to pronounce those names because they're hard. And this thing has a diameter of about 4 kilometers. So yeah, the key takeaway here is that comets are typically small, and these things are typically bigger. All right. So we try to find things in the outer solar system because they tell us how the solar system formed. I was telling you about this beautiful story where the planets form in different orbits and whatever, and then they migrate, and that's where they are now. And the reason why we know that is because we've been studying objects in the outer solar system and trying to figure out how they got to where they are today, basically. We know that they exist, so we had to come up with an explanation. And this is why we try to find these things. So this was basically my PhD project, was developing a methodology to discover these things in a project called the Dark Energy Survey. As you can imagine from the name, this is not a solar system project. This was a project that was made to find hundreds of millions of galaxies and understand basically how the universe worked. But one cool thing is that the sky is just one thing. So every time we take an image of the sky, we're seeing not only galaxies and stars or whatever in the background, we're also seeing things close by. So we see asteroids, we see Trans-Neptunian objects, and unfortunately, we see things like starring satellites. So DES started taking images of the sky in something like 2012. It took images during 6 years, and we covered basically one eighth of the sky. So it's a pretty big area. DES is a large international collaboration. We have people from 8 different countries. I don't remember all of them off the top of my head. But one important thing is that there's a lot of people in the US for DES. This is the telescope that we used. It's the Barclay Telescope in Chile. It has a 4-meter diameter, and it has a very beautiful camera that is showing this image here. It's called the Dark Energy camera. And This camera has something like 500 megapixels, so you can imagine taking multiple copies of your iPhone camera and placing them on the same thing and taking an image of all of them simultaneously. This is basically what this camera does. And this is what our images look like from, from DS. This is one of the images of the discovery of one interesting Trans-Neptunian object that I found. And if you look at this image, it's quite obvious that you can't really see what is going on here. There's a bunch of stuff, and you can't really identify what is going on. So let me try to make life easier for you, and let me walk you through where the thing is. So the thing is in this little square here. This is one of the smaller pieces of camera that we have in this thing. And let me zoom in. And you can see that there's still a lot going on. There are stars everywhere. There's this galaxy here. There's a cosmic ray that is something hitting the camera and giving a weird shape. That's something we don't want in our data, but we can get rid of them. So basically, in images like this, we have to try and find something. And this is where the object is. And I don't think you can see it. I believe I do, but that might just be because I know where the thing is. So let me zoom in again. And this is what the thing looks like. So, if you think of that image of Pluto that you had in your head that I showed a few minutes ago, and this is quite disappointing. Because I can really see a thing here. It's not just the projector, it looks better on my computer screen as well. So yeah, we have images of this thing from 2014 to 2015, and if I basically combine all the images, it looks like this, and it's still incredibly disappointing. That's part of life. Welcome to astronomy. Things don't look pretty. You were lied all your life. No, that's not true. Some things look pretty in images. But yeah, so this is a video that we put together to basically explain to you how we find things in our data. As I said earlier, this project is not meant to find things in the solar system, so we have to work hard to do that. It's a large computational problem. Let me start the video. So the idea, and just see if the videos work. Yeah, the videos work. So the idea is that we have to find things that are moving between images. What happens is that things on the solar system, they don't stay in the same place during years of observation. They move. This is a combination of both the object moving around the sun and also the motion of the Earth. So that's why the things move in the images. And they look something like this. We have to basically find where these things are and try to find in future images and see if the positions that we have measured the object make sense with something that is moving in the solar system. So we had this catalog of things that are probably moving. We did a technique that is basically the spiritual successor to what Clyde Tombaugh did in the 1930s to find Pluto. Where we basically were comparing multiple images to see if something moved. Of course, we did this using computers and not by eye like Tombaugh did in 1930, but yeah. And then we played the world's hardest connect the dots problem, where we basically went through all the dots and saw if they had something else that looked like a real solar system orbit. And I said that this is a massive computational problem, and this took us 20 million CPU hours. If you're not used to this term, CPU hours, this means that I had to leave a single computer working on this problem during 2,000 years to solve this problem. Of course, I didn't wait for 2,000 years because it didn't start this project when Jesus was alive. But we solved this by using basically hundreds of computers. And yeah, once we find these things and have multiple detections in our images, we can go ahead and try to say what the orbits of these things. So this is what this pre-video is showing, basically. And you can see that there's a lot of stuff going on. We find things basically where it lives on the sky, and then they go everywhere. Well, traz minha cerveja. Sorry, I was just asking my wife to bring my beer. Sorry, my throat is a little bit too dry. But yeah, once we finish this thing, after finding, after going through millions and millions of different combinations of something that looked like a real solar system object, at the end of the day, we had 814 things. And as I said earlier, we know about 3,000 Trans-Neptunian objects. And so this is basically saying that I found something like a fourth of the total, which is, pretty impressive. And something I'm really proud of. Just to give you a sense of scale, because this image is rather confusing if you've never seen anything like this before, each line here is showing the orbit of one of these things in the solar system. And here is a zoomed in view. So I'm going from this little circle here to this thing, which is showing basically the closest things we found in our data. So here's Neptune, and then the other planets that I don't really care about. And then this purple thing here is the Kuiper Belt. So this is the bulk of the Trans-Neptunian region. This is where most of the things that we found live. So yeah, you can see that there's a lot going on here. And maybe you've already seen it, but there's something that doesn't look like the rest of the things here. This thing has a completely different orbit, which means that there is something quite interesting going on here. So let me zoom out again, and this is what the orbit of this thing actually looks like. So we're going from here, where Neptune is, to here, which is what the actual orbit of this thing looks like. So this is an orbit that comes from the Oort-cloud. The Oort-cloud, as I said earlier, it's basically a spherical region. We know that things come in from there because we see them, but we have never actually seen something in the Oort-cloud. And the reason for this is that things in the Oort-cloud are small. And because things get incredibly far, as you can see here, so the farthest point of this orbit is something like half a light year. So this is really far from Earth or anything else close into the source. So we basically catch the things if they come close to us. Yeah, so this object, it has its closest point in the orbit to the Sun in 2031. So this means that we have another 9.5 years to observe this thing before it actually reaches its closest point in its orbit. And then we have another 10 years before it gets too far for us to be able to actually see it. And this is at a distance of 10.9 AU, basically. This is a little bit further than Saturn. Saturn's distance to the Sun is 9.7 or something like that AU. It's a number that I know it's around that thing, but I don't really know the number. And this thing has an orbit with a period of about 3.5 million years. So basically, the last time that it came close to the solar system was 3.something million years ago. And then we have another 20 years to observe it, and then it's gone. We'll never see it again. This is one of the sad things about observing comets. We don't really have a lot of time to watch them. Typically, we have something like a year or two before they get too far from the Sun, and we don't see them ever again. In the trivia, they were talking about Hale-Bopp, and basically Hale-Bopp we could see from the naked eye during 2 years. I don't actually know the number of months where it was visible, but we saw it from 2 years, and now it's gone, and we'll never see it again. This is another case of something like this happening. In 2040, this thing will be impossible to observe and will be gone, which is a little bit sad, but that's part of it. So why is this thing a big deal? We know that comets exist. We know of thousands of them. And people find comets basically every week. The reason why this is a big deal is because this thing is incredibly big. So these are the two largest comets that we know of. The first one is Hale-Bopp, that was discovered in 1995, that has a diameter of 74 kilometers or something miles if you use this barbaric unit system. Sorry, I'm not American, so I'm not used to miles. And the second largest comet is this comet here called Theraband. This was discovered in 1729 by a French priest, I think. And this is the only image we have of it. So, 300 years ago, we didn't have digital cameras. So these things were drawn by eye with incredibly detailed precision and etc. And this thing had about 100 kilometers of diameter. We don't really know if this is the right number because basically people were seeing this thing by eye. So they had to estimate how bright the thing was. So it's obviously not precision science like we're used to today. And why are these things so rare then? The reason is that I showed you earlier the protoplanetary disk from the solar system. The processes that went through there formed a lot more small objects than big ones. Basically, there are some complicated physics that I don't really understand, and most people don't really understand, that go through these things, and we form thousands of small objects and just a few big ones. So in other words, big objects are rare in the solar system. That's why we only have 8 planets, but millions of asteroids, basically. And then there's this comment here. This is the image. I told you that images were going to be disappointing, and this is another one. Even though this is a really pretty image, the actual comet is just a dot that you can barely see in this projector. And a few cool things about this comet. The first thing is that it's exceptionally bright for its distance, and this is already telling you that the thing is pretty big. When we see something in the solar system, we don't really see it emitting light. We see the light that reflects from the sun. So if the thing is bright, it means that it's big. This is rule 1 of observing things in the solar system, basically. And also, this happens to be the most distant comet ever found. This was found at a distance of 29 AU, which is basically Neptune's distance. And most comets are found when they get closer than 5 AU from the sun. So this is why I'm saying that, hey, it's cool. We're going to have like 40 years, 20 years to observe this thing until 2040. This is the reason. We found it extremely far from the sun, which is something that doesn't happen every day. So this is quite amazing. And I told you that this thing was probably big. So by combining both data taken with optical telescopes, this image here, and with thermal telescopes, which is this image here, we've been able to determine that this comet has a diameter of 137 kilometers, which is basically twice as big as Hale-Bopp, which makes this the largest comet ever found, which is, you know, something cool to say that I was able to do. Oh, by the way, an interesting thing about rules of naming comets, comets get named after their discoverers. So, you know, that's why this thing has my last name. Yeah, I get to brag about that. That's cool. This is a nice image that gives you some context about on how big this thing is. I showed you earlier Comet 67P. This is that comet in the image. I also showed you Arrokoth, and that's where this thing is. And this is Enceladus or Enceladus, I'm not sure what is the proper pronunciation, one of the moons of the giant planets in the solar system. And this is this comet that I discovered. So this thing is pretty big. It's almost as big as the moons that we see in the giant planets. And once again, these big things are rare, so this is quite a fascinating find. And it has attracted a lot of attention, both from professional and amateur astronomers. I'll show you some images later on, and also from media. During the second half of last year, I think I gave something like 50 interviews to journal news articles and etc. everywhere. And it was, you know, honestly quite annoying because every day I would get an email from someone saying, hey, I'm a journalist in journal whatever. Can you talk to me about this thing? And, you know, the first 10 were fine, but after several of those, it got a bit tiring. And yeah, so I'm going to skip this slide for now. I'll go back to it later. This thing got announced mid-June last year. I think it was June 19th. And within a few days, basically everyone that had a telescope ready took an image of it. So this one was taken June 19, June 24. This one was June 22nd. So basically people that had access to telescopes took images of it, which was something quite fascinating. And let me go back to these images here. These were images. This is a combination of images taken by the Dark Energy Survey. And once again, it is really disappointing compared to what you would expect to see from a comet. In particular, because in these images, you don't really see the tail that you would expect to see in a comet. And this was something that puzzled me for a really long time. This thing is really a comet. We know from its orbit. We know from images taken nowadays that it has even a little tail here. I don't know if you can see it. It's a bit hard, but It does have something like that. So why are we not seeing it in these images? And it turns out that the tail of this thing is incredibly faint, and it didn't develop until it was at a distance of about 26 AU. So this is an image of the thing at 26 AU. Get closer, and you can see something a little bit here. This is really faint and really hard to detect, and that's something that we're quite happy to see in the data, because basically we saw a comet turning on. And this is the first time that we see something like that. Once again, because we only see comets close to the sun, we only see them when they're well developed. So this is basically the first time that we've ever been able to measure something like that. And these images that are, from 2021 are way prettier than these ones. But yeah, that's basically all I had. We can chat and talk about this thing. So just to summarize what I've talked about, this is an incredible comet that was found basically by accident. We were looking for a different type of object, and we found this thing because it was there, which is something that happens a lot in astronomy, but it's always cool when it happens. And we have a chance to study this comet in detail for the next 20 years or so, until it's gone and we'll never see it again. And if you follow XKCD, the proudest moment of my life was when XKCD with this comet showed up. Thank you. Yeah.
All right, thank you so much. She'll say Pedro, please round of applause, but all right, so what we're going to do now is announce trivia. So I'm going to put this microphone down for a second, and I'm going to go up and switch our slide to the trivia slide so I can walk through the answers. And then I'm going to announce. Let's let Pedro answer some questions first. My mistake. Sorry about that.
No problem.
Yeah, so if anybody has questions, I'm going to give the mic back to Pedro, and I'll just let him handle the question and answer period.
I'll just pop up when
Okay.
you need to
Yeah.
move on.
Yeah. All right. If anyone, okay. I think it's easier if you walk here and speak on the microphone so I can actually hear you. Yeah. So stay on the microphone so everyone hears you as well. If you will just want to shout, and then I can repeat it. All right. That is a good question. So the question is if there is a maximum size that a comet can be. And the answer is we don't know. Let me go back a few slides. This thing is 95P Chiron. It's a centaur. It means that it inhabits basically the region of it where the giant planets are. And this thing looks like a comet. It has some things that are called activity. It has outbursts, which basically means that it's kicking ice out. And this is something like 200 kilometers in diameter. So this is the largest thing that we found that has this type of thing. But we don't know if there's a maximum size. Anyone else? Come as close as you want and then shout. It's easier.
3,000 objects in the Oort-cloud or Trans-Neptunian, sorry.
Yeah.
Oort-cloud is quick. But so you found about 3,000 objects. Do you have an idea of how many there are, like total? Do you have an estimate?
That's a good question. So the question is how many there are total in the Trans-Neptunian region. And we expect there to be something about 100,000 of these objects, larger than 10 kilometers or so. We don't really know the number. This is somewhat of an observing effect. It's hard to find smaller things, and there are more smaller things than big ones, but also because we haven't really measured the entire sky for these things. So yeah, the expected number is on the order of 100,000, and in the next decade or so, we are trying to find something like 50,000 of those. So we'll know, in 10 years, what is the actual number.
Eventually burn up and disintegrate?
So the question is if comets eventually do burn up and disintegrate, and the answer is yes. As they get close to the sun, they warm up and start sublimating ice. And the closer that they get, more material is evaporate, and eventually they just disintegrate. We have seen that. I think there was a comet that was measured to be disintegrating last year, if I'm not mistaken. And that's something really cool that we see in the images. We basically see, we take an image of the thing, it's in one piece. We see a few months later, it basically has a bunch of pieces, and that's something that's quite hard to track. Comets also die if they hit the planet or they hit the sun. That's a bunch of things we have measured as well. And also, because these things are losing mass, they basically speed up a little bit, and they can be ejected from the solar system. So they don't really die, but they basically never come back because they were kicked out of the solar system. So the question is, what type of observation you need to determine an orbit, right? To determine an orbit of these things, you basically have to see it moving. So let me go back a couple of slides. So to this slide. This is a bunch of images taken between November of 2011 and, 2014 and December of 2015. So this is the type of thing that we need. We need to see it across a few months, and then we're able to actually tell that it's moving. So why do we need to see across a few months and ideally between different years? The motion of these things is dictated on the sky, is dictated by the motion of the Earth. So basically what we see when these things move is a projection of the motion of the Earth. So if you see it across different years, you're basically seeing the Earth, seeing this object from different places. And that's how you can track it down. But ideally you need something like several years of data to be able to say really well what the orbit of the thing is. So the question is what to look for in 2031 for this thing. And the answer is that there are several things that we're trying to do with this comet. So the first thing is we're trying to determine what sorts of materials it has in its surface and what materials are being evaporated. The idea here is that once comets get closer than 5 AU, they start sublimating water, and that's how we thought of comets until something like 10 years ago. Now that we know the comets have activity up to 20-something AU, and only a few of those have been seen, we don't really know what type of material causes it. So that's one of the things that people are trying to figure out about comets, is what type of ice that we have in this object that makes it evaporate as far from the sun as 20. So this is one of the things that we're looking for. Of course, because we have a lot of time, we can also do things like see how its brightness changes as a function of time. For example, if it's rotating, its brightness will fluctuate. And that's another thing that we're trying to do nowadays. So basically, is it rotating, what sort of shape it has, and all sorts of questions like this.
Goal of the deep sky of the dark energy. What was your motivation for doing this relatively complex analysis that ended up finding?
That is a great question, and the answer is it's basically what my PhD was. So the question is, what was the motivation to do search for objects like this, given the original goals of the Dark Energy Survey? There are a few ways to answer this question. The first one is basically we knew we could, so why not try? But also you need some sort of a deeper motivation than just we can do this, right? So a few years back, there's been this discussion about the possibility of a ninth planet in the solar system. That's something that's still an open question in the field, and I've given astronomy talks about this, so I won't say too much about it here. But the idea is that there might be a ninth planet in the solar system that we haven't found yet. And one of the motivations of trying to find objects with DES was that we could basically try to search for the thing directly, or if not see it, basically say a little bit more if we expected it to exist or not. Our answer is that it's not there, not just because we didn't find it, But because we've done some analysis saying that, hey, yeah, if this thing existed, things will look different in the solar system. So this is one of the key pieces of motivation. But this is one of the beautiful things about astronomy, is that when we have these large sky surveys, we can do lots of different sciences with it. With DES, we've done the solar system stuff that was very rewarding, but we've also found lots of different structures in the Milky Way that have never been seen before. People are finding all sorts of weird galaxies and etc. So that's what you get when you measure, basically one in the sky. You get to see all sorts of things that you don't expect. One more question. No one? All right. Thanks, everyone.
Thank you. Okay, so for that time, that's 3 big rounds of applause for Pedro. Let's do one more. Okay, great. Now, is our very own UW Astronomy grad student, Andy Zenadakis.
Woo!
Andy is a first-year astronomy PhD student at the University of Washington. Andy's research focuses on the observational properties of stars using large data sets. An ideal evening for Andy, in case you wanted to know, includes cooking Greek food, not just cooking Greek food, eating donuts, and communicating science with the world. And that's all of you. So give a big round of applause for Andy. And then afterwards, get up here, Andy.
Thank you.
Forward, backward.
Cool. Thank you. All right, let me just put this away. Cheers, everybody. You hear me? Nice. All right. Yeah. I'm gonna need a couple more beers here. All right. How are y'all doing tonight? Yeah. All right. Let me just hold on. Microphone is falling off here. Give me a second. All right. Can anyone hear me in the back? All right. Good. All right. So let's get started here. So today we're going to talk about fields of astronomy you've probably never heard of, right? Celestial cinematography, right? Pretty strange word. We're going to talk about the dynamic universe, and I really want to take you on a trip into the universe. Perhaps like a new lens of really viewing the world around us, and especially the universe. So let's get started here. And I really want to take you on a journey to a place in the universe that you might not expect. Okay? Now we got a raise of hands here. How many of you have been to New York or have lived in New York? Yeah, New York is awesome. Yeah, I love New York. I'm from New York, so. Okay, so here's the question I have for you all. Right? Suppose you had this image of New York, and I asked you, does this picture fully represent the spirit of New York City? Or any big city, really, right? No, right? Well, it looks a little suspicious, right? You have some like happy people walking around, but as any New Yorker would tell you, that's never the truth, right? You can see some taxis and stuff like that, right? But that's really not the full picture, right? You need something more, right? Okay. The reality is that New York is this dynamic place, right? The center of so many cultures and people coming together, right? New York's a great place. And any good New Yorker would tell you that no 2 days are the same, right? So a lot of weird stuff are happening in New York, a lot of exciting things. Like, for example, you have rats stealing your pizza. Like, that's pretty messed up, yeah? You have commuters, like, putting their pets in, like, I don't know what that is. But yeah, I'll go with it. And you have people dressed up as Christmas trees in the subways. I mean, like, I'm not making this stuff up. Like, if you've ever been to New York, like, this is actually, like, real life. But the point I want to make here is that no 2 days in New York are the same. And so therefore, New York is this dynamic place. Many exciting things are happening at once. And so, yes, you predicted correctly. I will say that the universe is very much like New York. And that's possibly the most New York thing I've ever said in my entire life, right? If I asked the astronomers here in the room, or all of you, do you think that this picture here fully represents the spirit of the universe? The actual, if it gives us a full picture of what the universe actually is. What do you all think? No, right? Yeah, exactly. There's a lot more exciting things in the universe, and for many reasons, we see a lot of pictures of the universe, and they're just still images. But the main thing is that, oh, there's an alien here too. Yeah, it says waves high, right? There's a lot of things, exciting things happening in the universe, right? You could see stars, you could see galaxies, you could see all sorts of exciting things. But what I want you to remember from this talk is that the universe is changing, and the universe is changing with time. So my goal today is to kind of tell you this story of how we think of this changing universe and why this question is really so important, has taught us so many important lessons throughout history. Okay? So we're gonna kind of take a journey here and really understand a lot about this changing universe. But remember that the universe is always changing with time. Okay. So, all right, you're like, hold on, Andy, you're giving me too much information here. You're telling me that the universe is changing. Like, how did we even get to that conclusion? That's a lot to process. Okay. So don't feel bad because people have only known about this for 2,000 years. So you should get onto this. But yeah, humans have really been observing the night sky for more than 2,000 years. But we've been seeing documentations of things happening in the night sky for over 2,000 years. So Chinese astronomers in the Han Dynasty would see these stars that would, well, they call them the guest stars, right? And they would be as bright as a full moon, and they would last for like a few months. Indigenous Americans would see things where they documented here. I don't know, this point is right over here, and they signed it too. Like, hey, we saw this first. But the point is that throughout the history of time, we've seen a lot of things change in the night sky. And what I want you to remember from this is that in order to see the night sky change, right? You're like, Andy, like when I go outside, like I look at the stars and nothing changes, right? Like it looks like the same old boring sky, right? And you're like, well, the point is here that you actually need to look for a long time to actually things change. And you really need to be staring at the night sky in order to see these changes happen, okay? So we're going to go through all of these different kinds of changes that we will see. Okay, so a few moments later, and by a few moments later, I'm talking about more like 1,000 years or so. We're gonna kind of zoom out. We're gonna take a little tour of our universe. Okay, so right now we just left New York City, so buckle up, and now we're in the solar system. So welcome to the solar system. All right, so now I picked a particular story that I loved. Okay, so here we go. 1930, American astronomer Clyde Tombaugh, right? Here he is, looking pretty good with his telescope, all chill. Clyde found something. Now, in the audience, if you know who Clyde is, please don't ruin it for the rest of us. But Clyde found something, and I really all want you to get that experience of joy of what Clyde found. Okay? And so, a little bit of context. At the time, he was using these telescopes, and he used these photographic plates that you would put on these telescopes, and you would take pictures of the night sky. And he used this machine here, which is called a blink comparator. And all that is, it's basically you take two images. Back in the day, you took photographic plates of the night sky, and you can compare the two images to see what would change. So Clyde did this, and he found something. So this is not part of the official trivia, but I want to see if anyone can find what Clyde found. And again, don't spoil it if you could see it. Okay, so I'm going to show you two series of images. Warning, there is some flashing going on, so if you're sensitive, please look away. And try to see if you could find what Clyde found. Okay? One thing before I go. Between the images, you'll see that the night sky is kind of, these stars that we're seeing here are going to be kind of changing, right? And one thing that we need to keep in mind is that the weather conditions that when you're taking these pictures is not always the same. So that's why you might seeing like all sorts of weird stuff happening with these stars. Okay, so are we all ready? Okay, so when you see it, maybe raise your hand and I'll maybe call on you to ask you where it is, okay? All right, ready? Go. Do you see it? Where? Oh, let me get someone. Where? Maybe someone in the back. Scream it out loud. Is it like in the center, bottom, where? Bottom left? Yeah, I'm not authorized to tell you what that is. Where? Upper middle. Okay, okay. I hear some good thoughts. Okay, so upper middle. Yeah, woo! Yeah, you passed the astronomy test. Good job. Good, you get A+. By the way, do you know what you just discovered? A planet at the time, though. Just to be aware, right? Unfortunately, Pluto is not a planet anymore. Let's get past that. But you know, Pluto's a great system, you know. Yeah. Poor Pluto. Okay, so obviously, you know, Pedro's talk really motivated this idea of like, why do we need to study the solar system, and why does the solar system really contain all these bodies that we could study? And really, you know, there's a myriad of many asteroids and meteors that are going around our solar system, and so even our own neighborhood, our solar system, is really dynamic. There's a lot of things going on. And I really hope I don't need to motivate why it's important to know like where all these asteroids are and what they're doing, right? Like I don't know if you've ever heard of this story before, but yeah, we definitely need to know where they are. So that's one important thing. But kind of on a more serious topic, right? We want to take an inventory of like where all these asteroids are and meteors are, because that gives us an idea of, you know, the formation of the Milky Way. Some of these objects are as old as the solar system. So understanding where these objects are, studying their light and how it changes, right, can tell us a lot about the shapes of these objects and possibly about the solar system itself. Okay, so we're going to zoom out even further now. Now we're going to go into the stars. And stars are my favorite topic. Stars are like the coolest thing ever. Okay. So our story here begins in the early 1900s by Henrietta Swan Leavitt. She was an incredible American astronomer. And so around that time, her collaborators and her were studying these bizarre stars in a neighboring galaxy, which was called the Magellanic Clouds. And so this is obviously not to scale, right? But our galaxy, turns out that we have these neighboring dwarf galaxies that are kind of going around us. And so they were studying the properties of the stars and how these stars changed. And so at the time, they realized that something weird was going on. So this is an image of a galaxy of these stars. And what you'll see is that these stars are flickering. Now, let me give you a little bit of context, right? At the time, astronomers didn't know that much about stars. So this was kind of like next level stuff. Like you see this and you're like, oh crap, like I don't help me here. Like it's really difficult to understand. So it turns out that what they were looking at is a kind of stars which are called Cepheid stars. And Cepheid stars are kind of these interesting stars. And here I'm going to show you a diagram of the brightness of the star as a function of time. So you're just tracking basically the brightness. So let's see what that looks like. So what they found was that the star actually has this sort of periodic behavior, right? It becomes bright and faint and bright and faint, and it really just completes the cycle. But one of the most amazing discoveries at the time was that Henrietta realized that if you were to look at the cycle that it takes, the amount of time that it takes to go from one top, right, to just complete one full cycle, right, that almost perfectly correlates with the brightness of the star. Now, you're all looking at me like, all right, like, what does that mean? Like, complete silence. But the astronomers in the room know that that's actually really important, because what this means is that we can actually measure the distance to these stars. And so these Cepheid stars become like a measuring stick in our universe. And distances in astronomy are really difficult. It's a very sore topic. You know, if you ever want to like get an astronomer like all like uncomfortable, you just tell them like, how do you calculate the distances in the universe, right? And so this was a pretty big deal that she discovered. So this is a really important thing. But a few years later comes another dude, Edwin Hubble. Does that ring a bell? Yeah, so Edwin at the time hears about this discovery and he's like, all right, like cool, like that's a pretty neat idea. I think at the time he was working as like a janitor at the Mount Wilson Observatory, and then eventually like convinced like the person to like let him observe these stars. So Edwin Hubble was interested in looking for these stars in distant galaxies, and he was actually the first one to realize that the closest galaxy to us, the Andromeda Galaxy, was actually a galaxy in the first place. Fun fact, if you're ever in Los Angeles, California, go to the Mount Wilson Observatory. It's on a 100-inch telescope, single piece of glass. The thing is ginormous. And on public outreach nights, they even let you like even look through the eyepiece. And so you could tell your friends that you're a cool astronomer or whatever you want to say. Okay, so Hubble, oh, I guess that gives the punchline away, but anyways. So Hubble makes this pretty interesting discovery, right? Using this concept of these Cepheid stars. So he tries to discover these Cepheid stars in distant galaxies. So here I'm going to show you a diagram of the velocity, so how fast things are moving away from us, as a function of distance. So distance and velocity. Okay. So Hubble begins to do his search on these Cepheid stars, and because we can measure the period of these Cepheid stars, we can kind of infer a distance and measure their velocities. Okay. So, the first few data points come in. Yeah, looking good, looking even better. Oh crap. There's a straight line. Now, for my astronomers out there, when you have things that look like a straight line, it's a good day. The universe, when you can express the universe in a straight line, that's a good day. But what Hubble really found was that, punchline, the universe is expanding. The further away we looked into the universe, the faster things are moving. And so this is a fascinating discovery, right? And so we went from a simple concept as the changing night sky to an expanding universe. So really take a second to internalize how amazing that is. Okay. An analogy that astronomers love to give is that imagine if you were baking like bread with raisins. As you're baking the bread, the separation between each the raisin would increase. But I hate to use this analogy because it makes me really hungry. I really like bread, so yeah. So there you go. Okay, but obviously there are a lot more stars than just your simple Cepheid stars, right? There are all kinds of stars, and this diagram is pretty complicated to explain, right? This is basically like color and like brightness. But the point here is that there's many, many kinds of stars. Our sun is a pretty ordinary star. It's called a dwarf main sequence star. But there are all sorts of weird things, right? There's like red giant branch stars but the point is that when you look at the brightness of these stars as they change, they could tell us a lot about the physical processes that govern these stars, and can really give us a lot of insight into, what are the physical mechanisms that govern these stars. So a lot of stars out there, a lot of things to learn about the changing night sky. So there's not only Cepheid stars that are changing, but there's many different kinds of stars. So we can apply the same concept too. Okay. We're going out now even further. Now, you're like, Andy, okay, what else can change in the universe? Okay, we have stars, okay, maybe galaxies. Do galaxies change? Let's see. Okay, here's a pretty amazing statement. Let's get a little silence here. Every second, there's at least one star in the universe that's going boom. Can you hear it? No, I'm messing with you guys. You can't hear it. Okay, so this is a pretty big statement, right? But what does this even mean? What is a supernova? What's going on here? Okay, so at the time, this was a couple of decades ago. There's this Swiss astronomer his name is Fritz Zwicky, and his name he's a pretty controversial figure. He used to call astronomers spherical bastards. If you just Google that term, it's basically that no matter what way you look at astronomers, they're bastards. Very, very strange stuff. But nonetheless, he was a genius in realizing that the only way we can really understand the changing night sky is that if we actually use our telescopes to kind of survey the sky. We really need to have an unblinking eye in order to catch these amazing things that are happening in the universe that are changing. And so, him and his collaborators started this survey to look for, all sorts of supernovae that are taking place. And fun fact, these are some no, there you go. These are some supernovae that I discovered, right? It turns out that Fritz Zwicky was right. It's amazing. You could discover these things all the time. So, you could discover supernova, everyone can get a supernova. Yeah, pretty cool. Okay, what are supernovae in the first place? That was the other slide. Okay, so there are flavors of supernova. I swear to you, this is not an ad for ice cream. Yeah, it looks kind of, I don't know. I don't know what my thoughts here. But anyways, so there are two kinds of supernova. you have your thermonuclear supernova. So this usually involves, and this is again theoretical, but this involves two stars, and you have usually one really big star that's donating mass to a compact object, and then as it's accreting all this different material, it's sucking in all the material. Basically, you can get these explosions because it reaches really high pressures and temperatures. And then on the other side, the core collapse supernovae are these really big stars, right? And when they reach the end of their life, they no longer have fuel to kind of maintain the gravitational pull of their own gravity. So they collapse and they go boom. And so those are the two flavors. If you've ever heard of the phrase "we are made out of star stuff," well, here you go. This is what star stuff is made out of. So you get a star stuff, everybody gets a star stuff, right? But these are one of the main reasons why we think that the universe has so many different kinds of elements, right? The oxygen in your blood, the nitrogen, and all different kinds of heavy elements are producing these enormous explosions. How do you even discover these, right? Like that's a pretty interesting question. So the way you do this is you use a telescope, you look at some patch of the sky, and let's say we have an image before. Let's say we had an image from like last night. And now I'm going to take a picture tonight. Like let's say like one night after. So you have like a before and after. Now in the hypothetical world, if nothing had changed, these two pictures, like if you subtracted this image from the other, this would be 0, right? Because nothing has changed. If nothing has changed, you basically get 0. But in fact, you get a little dot. And that little dot is a supernova, right? That's really that. That's how easy it is to discover supernova. So yeah, everyone can do it. Yeah, we need help because there's a lot of them. Okay. But my favorite fact about supernovae, right? A single supernova explosion can produce the energy equivalent of our sun after 1 million years. So imagine if the sun was burning for 1 million years, a supernova could release that in a matter of like days or hours. So if you've ever had trouble sleeping at night, don't worry. The universe always has your back for the scariest shit that you could think of, right? Yeah, so yeah, take that. The earliest supernova, actually the supernova we've known for a while now is 1987A. This was the closest one, the most recent supernova that we've known about. And the question is, can you even see where this is? So this is actually in the Magellanic Clouds. So there's a neighboring galaxy, not even in our own galaxy. But can you even see where the difference is in this image? Yeah, okay, yeah, I just trust you. Good, yeah, so that was the most recent supernova that took place. Pretty cool stuff. Yeah, so astronomers got really excited when that happened. The point is, though, that it turns out that supernovae are not the only kinds and flavors of explosions. And it really is that there's a lot of kinds of explosions, right? So supernova in this diagram, so this is a diagram that tells us something about how long do these things last for. So over here you would have like 100 days, and then this is the vertical axis is just telling you about how bright they are. So the supernova we just talked about kind of are just around here. Now you might have noticed I put some emoji symbols of like money. So it turns out that we think that the most exotic kinds of explosions, which produce gold and platinum, are somewhere around here. And believe it or not, there are things that are even called koalas and cows of explosions, which are all kinds of different weird explosions that are really fast. So you see them for like a couple of days and then they disappear from the universe and you can't see them no longer. But what you might notice from this diagram is that this diagram is mostly empty. And this really gives us a potential to really explore all kinds of explosions that might tell us about the universe. And so our goal is really to understand, what kind of explosions are we seeing here? And this leads us to the final kind of topic of time domain astronomy, time domain sky surveys. Right? We need to use telescopes to understand what's going on in the universe. Now, I might have overwhelmed you a little bit about how much things are happening at the same time, and to be honest, like I haven't even told you the full picture. There's so many more things happening. So to overwhelm you even more, I want to just zoom in the Milky Way galaxy to just show you the scale of our own galaxy. So here we're just zooming into a picture, and you can see for each frame we're going through, we're seeing all sorts of stuff. So can you imagine keeping track of all of this changing? If we really made the argument that like the universe is really changing and there's stars and galaxies and supernovae and all sorts of things, do you really think that, how are we going to keep track of this, right? Like this was a pretty serious problem at the time. So how do astronomers do this? So imagine here we're seeing a view of the Milky Way galaxy, and we're within the Milky Way galaxy. So astronomers, what they do is that they survey the night sky. And all that is basically is that you can imagine that we have like these little boxes, and we basically scan the night sky. And we do this, you know, every night or so, right? We come in and we take a picture, and then you could basically compare these pictures from one night to the other and say like, huh, what has changed here, right? Is there anything new that's going on? So that leads us to this term that here I'll be using, alert. Basically, every time a telescope goes to the night sky, scans it, right? It does that technique that I talked about. It subtracts one image from the other. It could basically send you these alerts, right? Say like, hey, like things have changed. Right? So you have, let's say, an image here, which might be a galaxy, and that might possibly look like a supernova, right? So the telescope will do all the sort of subtractions and stuff like that, and you get these what we call detections. And then you could track that as time goes on, right? You can come back to that same point, let's say one tonight, one the next night, and then over time, we could basically track how bright these things are as a function of time. So here we're just seeing a core collapse supernova, and this might be on the scale of 100 days. And you can see this fantastic, like, huge explosion. Here it gets really bright, and then it eventually dies. And so this is the game that we play. Which leads us to the most important part of the night. So I really want you all to pay attention to this one. This leads us to the Vera Rubin Observatory. Now, this wouldn't be a complete talk if I didn't mention who Vera Rubin was. I'm going to put a bunch of points here. So Vera Rubin was an American astronomer. She is personally like my favorite role model in the field, and she has played such a huge, important role in female astronomers in the field. But she was the first female to gain access to the historic Palomar Observatory, which was a really big deal at the time. And one of the interesting things is that, so originally when we were going to launch this, we're going to talk about this telescope, was called the LSST. Congress decided to rename the telescope as the Veracy Rubin Observatory, named after the American astronomer Vera Rubin. And at the time, Vera Rubin had made a really, really important question and discovery. And this is, you might have heard of it, dark matter. That's a pretty big deal. Okay, so I want to really just go on a rant a little bit about what is dark matter. You might have heard of this story, but I really want to tell you about it really quick. Okay, so how do stars move around galaxies? Let me give you like an intro to like physics really quick. But like I promise you, this is the only equation that you'll ever see in this talk. But basically, the way stars move around galaxies just depends. So the speed of a star depends on the mass that's enclosed within the galaxy. So you can imagine that as the star goes around, the speed of that star depends on just basically the mass that's enclosed within that circle of its orbit, and then you divide that by the radius. Okay, pretty easy stuff, right? So here on the bottom, we have a diagram of the velocity against the distance, and it basically describes what we've talked about, right? We start, let's say, like a star starts at the center of the galaxy, right? Because there's not a lot of mass, it's not moving a bunch. But as you go further and further out, you're seeing more matter, right? There's a lot more stuff happening. There's more stuff in the galaxy. And then you go out into a point where you're so far away from the galaxy where the speeds eventually drop. So Vera Rubin had the idea to look at the speeds of objects in the galaxy. And so, you know, they start out and you're like, okay, good. So these are their measurements. So like, all is good. All is good. This is a good day for astronomers. So all good. All is good. Whoa. What is happening here? That does not look right to me, right? So what's happening here is that, whoa, the speed of stars is not slowing down, but instead they seem to be fixed. And the only way you can explain that is that if you had more matter, right? Because as we're going further out into the galaxy, you don't have that, we don't see that much mass, right? And so the only way you can explain that is if there was some invincible mass that is dominating this galaxy. And so that's why we're seeing that the velocity of stars is not dropping, but instead it's almost holding a steady pace. Okay? So this was, this makes astronomers angry. This makes conspiracy theorists angry. You have aliens. I don't know. But the best explanation to this is, well, dark matter. There might be some matter that we just don't know about yet. And this is, by the way, an unsolved question in astronomy. So if you have any ideas, let me know. It's worth a lot of money, but cool. So this leads us to the final journey, the Vera Rubin Observatory. Fun fact, when astronomers use the word era, that's a really important thing, right? Like if you heard like era, like yeah, that's like really important. Okay, so we have this amazing telescope that many institutions around the world, including the University of Washington, is leading. And this thing is next level, let me tell you. You'll also hear me refer to this telescope as the LSST. It's the Legacy of Survey of Space and Time. But yeah, I'll be using these names exchangeably. So you have this telescope that's currently in construction, and it's going to be surveying the night sky in the southern hemisphere. So this is located in Chile, in the Sierra Pachón. And it's going to be looking at the night sky. It's going to be basically surveying and trying to see what things change. Here is a picture of the telescope. Beautiful. This is the night sky that it's looking at. I mean, it's basically almost done. And I really want to say that this wouldn't be possible for all the amazing engineers and scientists that have made this project come to life. And I mean, really, this is an incredible experiment that's going to be happening. So, the telescope is ready to go. It's mounted and stuff. You can see the observatory here in the beautiful North Andes. Some specs about this telescope. Now, obviously, we're all very excited about this telescope. You can ask any UW student about this. A lot of the faculty and students are working on science projects that this observatory is going to be making. But I want to really blow your mind on how next level this thing is. So, telescope is 8.4 meters, which is 27.6 feet. Gigantic, like, yeah. I don't even know how tall that is, but like really big. We're going to also be doing this 10 years. That's a really long time. So we're going to be looking at the universe for 10 years, and we're going to be making this incredible movie of the night sky changing for 10 years. And the best part, well, we expect that the first light is going to be around 2023, so next year. Great year for many reasons. And here you can even see some little figures that I put up, just how big this thing is, right? It's a gigantic telescope that will just do a lot of amazing science. Okay, so for all my nerds out there, I compiled some statistics for you guys, just blow the minds a little bit. Okay, so on an average night, the telescope will deliver 20 terabytes worth of data. I don't know, like, does that mean a lot? But basically, a smartphone wouldn't be able to even hold that much information. After the 10-year survey, it's expected that the telescope will be able to accumulate around more than like 15 petabytes worth of data. I don't know if that's like impressive for like my Amazon people here, but like, that's something. Like for astronomers, like this is a pretty big deal, right? Like we've been looking at like photographic plates and like really small data sets for a while. So this is very overwhelming for astronomers, clearly. Another thing is that we expect about 10 million alerts per night. So you better keep your phone on mute or else you will never be going to sleep because there's going to be a lot of things changing, right? There's 10 million is a lot, yeah. And hear this. You will be getting alerts of the sky changing every 60 seconds. So can you just imagine your phone like ping, 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 right? That would just be very annoying to think about. But that just gives you an idea of the scale of this project, just because we have such a big telescope and that we'll be able to probe the changing sky. Who do you think has the world's largest camera right now? Astronomers, yes, correct. So they're going to be mounting it on this telescope, this gigantic telescope. They're putting the world's largest camera. The camera is 3.2 gigapixels. I don't know if I've ever heard of that, but like it's 250 times more sensitive than your smartphone. So very, very sensitive camera, very big camera. The camera, I think, is like the size of a car. That's what they say. Really big camera, very impressive. Hear this. It will take 337 4K high definition TVs to display one image. Yeah, I know. Like that's very overwhelming. But okay, this is pretty cool. What do you think the scientists that when they were commissioning this camera, when they were testing out the camera, what do you think was the first picture that they took the picture of? A piece of broccoli. Yeah, now this might be here the most expensive piece of broccoli you've ever seen, the most expensive picture you've seen of broccoli. It's technically Romanesco, which is a kind of broccoli, I guess. But yeah, you know, like here are the scientists like putting the piece of broccoli in like the world's most expensive and like advanced camera that humanity ever built. Like, yeah, pretty cool stuff. You're never going to see a picture like that before. But the camera is pretty cool. The camera is truly a feat of technology. Just to give you a more a scale of like the mirror itself, one image will be able to fit 40 full moons. So take your full moon 40 times. That's a lot. That's a big patch of area. And I know this is more about the camera, but if you were to distance yourself 15 miles away from the surface of the Earth, you would be able to resolve a golf ball. Yeah, that's pretty next level stuff. And now we have these filters, and so this is going to be the first survey that's going to be doing this in all sorts of kind of filters. Obviously, there's many other surveys that have done this in other filters, but this is going to be including also all these kind of filters. And what these filters will do is that basically we're going to be looking at the universe not only in a single color, but we're going to be looking at different kinds of colors. And different colors tell us something about the composition of these objects that we're going to be looking at, tell us something about the physics of these objects. It can tell us all sorts of exciting things that we will learn from it. So this is just showing you how that mechanism would work. And you can block out the light to kind of see all different kinds of stuff. Okay. Which leads us to the full circle. Now we have finally arrived to a static image. And so this is perhaps maybe something what it would look like. This is from a different survey, but you can imagine this is what the universe would look like. But as you all remembered from this talk, the universe cannot be fully represented by this image. But instead, maybe after 10 years, the Vera Rubin Observatory will be able to transform this picture from that static image to something like this, where you have all kinds of things and exciting things happening all over the place. You can see stars, and you can see supernovae, and you can see asteroids flying all over the place. And the amazing thing is that over the 10 years that the Vera Rubin Observatory will be surveying the sky, we'll be making all these amazing discoveries about the universe. Which leads me to the last problem that I'll leave you all with. And this is called the needle in the haystack problem. Now, this is, of course, very overwhelming, and there's a lot of things happening in the universe. The universe is a very busy place. And so given our very finite resources here on the Earth, you know, we have, maybe you've heard of the telescope, James Webb Space Telescope. We have the most powerful telescopes in the world. These are very finite resources. And amongst the myriad of many, many different kinds of objects that we see in the universe in many ways is both ordinary and extraordinary. There are things that are happening that we kind of know about, but the question is, how will we be able to tell the things that are extremely unique and important, right? Because there's going to be just so much information happening. And so astronomers are really baffled by this question, and this is a question that astronomers are going to be working in the next decade as this telescope will start to begin to collect data. And so I really want you to think about all the amazing possibilities that we could discover. Really, the changing night sky is really full of discoveries and things that we just we don't know yet about, right? And so there's a lot of potential for us to understand things that we don't know about. And all of the things that I've discussed, the Vera Rubin Observatory will be able to answer and give us some more insight onto. So I'll leave this here. If you have questions, please make sure to ask me. But if I don't get to your questions, make sure to come and talk to me after. And thank you all so much again. Thank you. Okay. Oh yeah, questions. All right. All right. Go for it. Let's see. Do we have any questions in the audience? It's a lot. It's a lot to handle. You all did great though. Silence.
Come on, somebody ask something.
Yeah, come on.
Astronomers have a question.
I put to sleep everyone. Everyone's yeah. Here, question. Oh, what's the plan of handling all these alerts? That's a good question. Well, the good thing is that what we will be doing is that we'll be sending these alerts to kind of like a thing that I was introduced to. Is called kind of like the Facebook for astronomers. So you can imagine that we'll be streaming these alerts into these what we call brokers, and using these brokers, you can basically kind of do all sorts of science experiments. Now, I really only tapped the surface here of like all the amazing science that you could do. But you can imagine like if a group was interested in like supernovae, for example, you would only be looking for supernovae. So you could use these brokers to kind of use all sorts of parameters for the star and kind of say, okay, like I'm only interested in the supernova and using that. Now, one astronomer doesn't always deal with the whole data set itself. Right? So you look at a very specific thing that you're interested in. That's a good question. It's very overwhelming, for sure. Yeah. I'm sorry, you have to repeat the question. What was the question? Mm-hmm. Yeah, that's a great question. Yeah, this goes back to this needle in the haystack problem. Yeah. So the question was, how will we be able to rank sort of what's really important in the night sky, right? Let's say like, Andy discovers a supernova in this galaxy, but Tyler discovered that he really wants to see that galaxy. How will we prioritize these resources? That's a really important question, and we kind of haven't figured it out yet. It really kind of has this very complicated system of like, who has telescope time, who has more power to like say like, I'm going to use these fancy telescopes. But this is a serious issue, right? Because the thing is that the night sky is happening in real time. So let's say like I think that I've discovered a really cool supernova, and like I don't use like the most powerful telescopes to kind of investigate more about it, then that's a big problem. So astronomers are working on all sorts of algorithms that can tell us more confidently that like, hey, like this supernova is really important. So like I need to follow it up. And this is the information that I have. So we use like these certain criteria to kind of tell us like, yeah, that's very urgent. That's a great question. Yeah, one in the back. What's my most controversial prediction about astronomy? Or opinion? Crap. Dang. You got me unprepared. Well, I put James Webb over here, and I really think, have you all seen the film Don't Look Up? Yeah. That movie made me feel really uncomfortable because, like, it really highlights this point that, if we make these really important discoveries in science, right? I feel that sometimes we can overlook at how important something is. And so as James Webb has launched and we'll be collecting photons very soon, I worry that James Webb is going to discover something so important, but because of the way social media and people and politics works, is that people are going to overlook on these discoveries. So I think that it's amazing that you all have come here to support science and really advocate for this work, because it's really important that we really contemplate a lot about these things, right? It's really worthwhile. Yeah, it's a great question. Any other questions? Yeah, one over here. Oh, I love it. The typical space versus. Okay, so the question is, what are the advantages we get if we were like to stay like to put these observatories like on the ground versus like in space? Like you're like Andy, like why don't we send this thing in space? First of all, it's a very big telescope, and this is kind of a hard question. If you do have like $1 billion, like definitely send it our way, and like we'll make sure that we could put it into space. But the thing is that, right, it costs a lot of money. Another thing that you might not think about is, let's say if something goes wrong, then you're in trouble, right? Because then you would have to spend money to like send astronauts to fix the telescope. A lot of people don't know that when the Hubble Space Telescope launched, there was an issue with one of the mirrors. So we had to pay money for astronauts to go and fix that. And so one of the unique things is that if you keep your telescopes on the ground and we keep our night skies clean, away from light pollution. Yes, yeah, that's very important. We need to preserve the night sky, right? Then ground-based observatories have this amazing impact of being able to look at the night sky, and if something goes wrong, we can go to those telescopes and twist a couple of knobs to fix these telescopes, and for them to continue to look at the night sky. Because our goal here is to just stare at the night sky to see all these changes happening. It's a good question. Yeah, one question here. Oh, so one discovery or innovation that I would like to see in astronomy in my lifetime. Well, I really think that I would like to see the discovery of, I guess like to kind of put at rest what this whole deal of dark matter is. It's been really getting it's been going on for too long to just, we really need to get to the bottom of this. So, and the amazing thing is that this observatory, the Vera Rubin Observatory, will, the scale of this experiment will really hopefully give us more answers about what is this dark matter. What is even the context of how the universe came to be. So yeah, I think that this telescope discovering the properties of dark matter and dark energy might tell us a lot about the universe. It's a good question.
Last question.
Last question. We'll get to the final last question. Yeah. Oh. Sloan Digital Sky Survey, my favorite. SDSS. Well, SDSS is kind of like the little brother to this, right? This is kind of like what we're going to be doing with the Sloan Digital Sky Survey. The only thing is that we're going to be doing this on a much bigger scale, right? The Sloan Digital Sky Survey, obviously, there's different kinds of programs that the Sloan Digital Sky Survey is doing this. Another thing to keep in mind is that what the Sloan Digital Sky Survey is doing is that it's not looking at the light changing, but the composition of objects changing. And that's the spectrum, right? So instead of looking at how bright things are, which, this was the whole point of this talk, they'll be looking at the chemical composition. And the chemical composition can tell us a lot of more interesting properties, right? That's obviously, it's not only to alter the universe and just the brightness. So in a way, this telescope is going to be looking at the brightness. And the reason why we use all these different kinds of filters is to kind of understand maybe a little bit about the composition. You don't have a lot of information because there's only, there's a few filters that we use to kind of get that. So you can't get, the full composition of these objects, but you can kind of get an idea of what's maybe going on. But yeah, the Sloan Digital Sky Survey was an incredible survey, and it's still going on. All right, thank you all again.
Thank you so much, everybody. Let's give a big round of applause again to both of our speakers. And one final huge round of applause. I don't know if anybody from Peddler is out here right now, but they posted Astronomy on Tap for maybe 6 years now, since before I was here. It's been so amazing having such a wonderful place to hold Astronomy on Tap every month. So let's give a big round of applause to Pedro. Good. And with that, we will call to a close our first Astronomy on Tap in 2 years, our last at Peddler Brewing. Please keep an eye on our social media accounts for announcements about future Astronomy on Tap. We absolutely will be continuing to do this. This is going to be a monthly thing going forward, barring global emergencies. But keep an eye out. We'll let you know when the next one will be and where it will be. And thank you so much for coming out here on this cold night.